Suppose I will switch. Hello students, once again you're welcome to Wisdom Academy. Today we'll be looking at the momentum in physics. We'll be looking at momentum in physics, and without much ado, let's begin. What is momentum? We will talk a little bit of it, and then we look at our tutorial. Momentum is defined as the product of mass and velocity. So momentum is defined as the product of mass and velocity. Momentum M. Let's say let's increase the intensity of our writing. Okay. Momentum M is defined as the product of mass and velocity. Mass and velocity. So mass multiplied by velocity, I'll get momentum. So every object has mass, right? Every object has mass. So if we multiply it with the speed of the object, we get the momentum of the object. Meaning, objects that are stationary, whose speed is 0, do not have a momentum. Objects that are stationary, whose speed is 0, do not have a momentum. Momentum will also be 0 because momentum is the product of mass and velocity. So this momentum, we use a symbol that looks like P to represent momentum actually. A symbol that looks like P to represent momentum, which means momentum is mv. Momentum is the product of mass multiplied by the velocity, right? Mass multiplied by velocity, we get the formula for momentum. Mass multiplied by velocity, or mass multiplied by speed, we get the formula for momentum. Now, what's the unit of momentum? Remember, the unit of mass is kilogram, and the unit of velocity is meter per second. So the unit of momentum will hence be kilogram meter per second. The unit of momentum will therefore be kilogram meter per second. So this is going to be our unit for momentum, or Newton, or you can simply say Newton seconds. You can say Newton seconds. Okay? So the unit of momentum is kilogram, as you see here, kilogram meter per second, because mass is in kilogram and velocity is meter per second. Okay? Now we say objects at rest do not have momentum because their speed is 0. If your speed is 0, you do not have a momentum. If your speed is 0, if you are at rest, your momentum is 0. Remember, momentum is mass times your speed times your velocity is same as speed. The only difference is that one is a vector, the other is a scalar quantity. Okay, so when your speed is 0 and your velocity is 0, your momentum is also 0. You do not have a momentum. Okay, so now quickly let's take a look at our tutorial that explains the momentum, that gives us a clarity of momentum. Let's quickly take a look at this our tutorial. Okay.
This video is about the conservation of momentum. All objects in motion have momentum. Momentum is calculated using the equation. Momentum in kilograms meters per second is equal to mass in kilograms times velocity in meters per second. The symbol P is used to represent momentum. These two objects move towards each other and collide. Momentum is conserved. We are taking the right direction as positive and the left direction as negative. The principle of the conservation of momentum states that the total momentum before a collision is equal to the total momentum after a collision. The red object of mass little m is moving towards a stationary object of mass big M. The stationary mass has an initial velocity of 0, so an initial momentum of 0. The red object has an initial velocity of little u, so the momentum before the collision is little m times little u. After the collision, the objects are now moving away from each other. This means the velocity of the red object is negative, as it is moving in the opposite direction to before. The blue object is now moving, so now has momentum. Its velocity is big V and is positive, so the momentum of both objects after impact is given by big M times big V minus little m times little v. In this worked example, calculate the velocity of the van after the collision for 4 marks. First draw and label a diagram to represent all the information. Let's start with the masses, as this does not change during the collision. We must use different symbols for each mass and velocity so we don't get confused. The car is driving along, which means it is moving forwards at 20 meters per second. Adding arrows to the diagram is essential to understand what is happening in the collision. The van is reversing, traveling backwards towards the car at 5 meters per second. After impact, the car must travel backwards because the van was reversing. The car has a final velocity of 2 meters per second. We have got to find the final velocity of the van, so let's add that into the diagram too. It is very important to add all the information to your diagram carefully. The first step in answering this question is to state the conservation of momentum for 1 mark. Now let's calculate the total momentum before the collision. Momentum is equal to mass times velocity. For the car, this is 850 times 20, which equals 17,000 kilograms meters per second. It is plus 20 because the car is moving forwards in the positive direction. For the van, this is 5,600 times minus 5, which equals minus 28,000 kilograms meters per second. It is minus 5 because the van is traveling in the opposite direction to the car. Now find the difference between the two momenta to obtain the total. The total is equal to 17,000 minus 28,000, which is equal to minus 11,000 kilograms meters per second for 1 mark. Use the same method as before to calculate the momentum after the collision. For the car, this is 850 times minus 2, which is equal to minus 1,700 kilograms meters per second. It is minus 2 because the car is moving backwards to the left. For the van, this is 5,600 times the final velocity of the van. So the momentum after the collision is minus 1,700 add 5,600 times the final velocity of the van for 1 mark. The final step is to use the conservation of momentum to equate the momentum before and the momentum after. So, minus 11,000 is equal to minus 1,700 plus 5,600 times the final velocity of the van. Rearrange and simplify to get minus 9,300 is equal to 5,600 times the velocity of the van. Then divide both sides by 5,600 to get the final velocity of the van, which is equal to minus 1.66 meters per second for the final mark. This means the van continues reversing, but due to the impact with the car, does so at a slower speed. Show each step of the rearrangement so you are less likely to make a mistake. In summary, an object in motion has momentum. The equation for momentum is momentum in kilograms meters per second is equal to mass in kilograms times velocity in meters per second. During a collision, momentum is conserved. The conservation of momentum states the total momentum before a collision is equal to the total momentum after a collision. You must carefully consider the direction of motion before and after a collision. Don't forget to check out all our other fantastic revision resources.
Okay, so we've seen the first tutorial for this class. The first tutorial is explaining the momentum, right? So we say momentum is mass times velocity. Mass times velocity. And when two objects hit each other, we can calculate the total momentum before they collide and the total momentum of the impact after they collide. So the two objects, we can calculate the momentum of the first object and the momentum of the second object because the mass and the speed of each one is given. But if the second object is not moving, maybe like a wall, and we have the mass of the wall, the momentum will be 0 before collision. After collision, we'll see what happens thereafter. Okay, if you take a look at this, we have the momentum of this one is the mass of the ball, which is 60 times 10 to the power of -3, which is 0.006, and times the speed, which is 2 meters per second, which gives you a momentum of this value. And then this is for gram, 60 gram we convert to kilogram by dividing by 1,000. When you divide by 1,000, you get this value. So you multiply by the speed of the ball, which is 2 meters per second, you get this momentum, 0.12 kilogram meter per second. Okay? Either you say per second or you say second raised to power minus 1. It's the same thing. So what this means is that this ball is, the mass is 60 kilogram, okay, and the ball was moving, you shoot it, you hit it, was moving with a speed of 2 meters per second. Now calculate the momentum of the ball. So first and foremost, what we do, we convert this mass to kilogram by saying 60 divided by 1000. If you want to convert gram to kilogram, you say 60 divided by 1000, okay. If we divide this by 1000, we get 0.006, right? 0.006. Okay, we get 0.06, sorry. There's no second zero here. 0.06 kilogram. This will be the mass, okay, of the ball. Now for momentum, you know, we use P as the symbol for momentum. So P is the mass times velocity. Momentum is mass times velocity. So the mass of the object is 0.06 multiplied by the velocity or the speed of the object, which is 2 meters per second. So if we multiply 0.06 times 2, we get 0.12, right? We get 0.12 kilogram meter per second. The unit of moment, kilogram meter per second. So that's the momentum of this ball before collision, even before it collides with the wall. The ball is going this way, so we have to use this as positive. The ball is going to this direction, and then when the ball hits, so this is the momentum. When you hit the ball, the momentum of the ball in the forward direction. Now when the ball hit the wall, the ball starts to bounce back, right? Start to go in the negative. The ball is now traveling in the opposite direction. This means its velocity must have a negative value. So this is the first case when you hit the ball. When the ball hit the wall, the ball will start. Remember, the momentum of this wall is 0. Why? Because the speed is 0. The wall is not moving. So the momentum of this one before collision is 0. And even after collision is 0. So when you hit the wall, the ball will bounce off and it will go in the opposite direction. So the speed will be -2 now. The speed will be -2. So if you say the mass is same, the mass is still conserved, mass doesn't change. You say 0.06 times -2, you get -0.12. So the law of conservation of momentum says that the total momentum before collision must be equal to the total momentum after collision. So which means the positive on the right, positive on the left, negative on the right, it means total momentum equal to 0, which means it's the law of conservation, because it said the total momentum before and after collision must be equal to 0. The algebraic sum of momentum must be equal to 0. That's the law of conservation of momentum. Its momentum therefore is also negative for this one. The momentum, if you calculate this one, the momentum after the ball hits and the ball is going back, the momentum will also be 0. The momentum will be negative. The momentum will be negative. Why? Because the ball is going the opposite direction now. Okay, but the total momentum before and after is same, except that they have different values. Now let's take some example. Let's work some example. Determine which object has the most momentum. Right? They gave us a ball. And the speed of the ball. This is a racket for hitting that provides the speed, right? So this ball, like I said, we're going to convert to, is in gram, we're going to convert to kilogram by dividing by 1000. When you divide by 1000, you get 0.06. 0.06 kilogram. You get 0.0. The speed is 75 meters per second. Now this object is moving in this direction. The speed is 1.5 meters. It's slow. You can see the speed is very small. It's slow. And the mass is 3 kg. So this one has a huge mass, 3 kg compared to 0. Remember, this one is 0.06 kilogram. You can see this mass is very small if you convert to kilogram. 0.06 kilogram. Why? The mass of this one is very big. The mass of this object is very big, right? The mass of this object is very big. The mass of this one is very small. The mass of this object is very small. The mass of this one is very big. The speed of this one is super huge of the ball. The speed of this one is small. So we can calculate the momentum. The question says we should determine which object has the most momentum. So to do that is to calculate the momentum of each one. So we have to determine the momentum of the table tennis ball using the momentum equation, right? By saying momentum is equal to mass times velocity. So the mass of table tennis ball, the mass is 0.0. We convert this 60 gram to kilogram. We convert this 60 gram to kilogram, we get 0.06 kg, right? 0.06 kg times the speed, which is 75. So when we multiply 0.06 times 75, we're going to get 4.5 kilogram meter per second. We're going to get 4.5. So this will be the momentum of this tennis ball. Now let's calculate the momentum of the brick. Determine the momentum of the brick using the momentum equation. Remember the mass of the momentum equation for calculating momentum is mass times velocity. So this will be the mass of the brick is 3 kilogram times the velocity, which is 1.5. It also gives us 4.5 kilogram meter per second. So which means none of them has a greater moment. They have the same momentum. So we compare the momentum of each object. Both the tennis ball and the bricks have the same momentum. Even though the brick has a very heavy mass, it's heavier, it's bigger than the ball. The ball is traveling much faster speed than the brick. Now this means that the impact, they will both exert a similar force depending on where they hit and which time they hit. Okay, so they exert same impact because they have same momentum. Now let's go to the law of conservation of momentum. The law of conservation of momentum says that the total momentum before collision is equal to the total momentum after collision. That's the simple way of saying it. The law of conservation of momentum says that the total momentum before collision is equal to the total momentum after collision. Total momentum, like this. Total momentum before collision should be and must be equal to the total momentum after collision. So this is the law of conservation of momentum. So if you say this in the exam, you get it. Another way to say it is say in a closed system, the total momentum before an event is equal to the total momentum after the event. So another way to say it, okay? Say in a closed system, the total momentum before an event occur is equal to the total momentum after the event had occurred. So that's another way to say it, okay? A system in physics is an object or group of objects in physics. A closed system means that there are no energy that is being transferred into the object or out of the object. No energy is transferred into the system or out of the system, and there are no external forces that is acting on it. That's what we mean by a closed system in physics. Meaning there are no no interference, no energy is being transferred out, no energy is being transferred into the system. Okay, so the total momentum before collision equal to the total momentum after collision. Let's take a look at the more explanation on the principle of momentum. Now we have two objects, okay, because this is where they get interesting. We have two objects, one with a small mass moving to the right, and another one stationary with a big mass. Now remember the momentum of this object before collision. When you have two objects like this, we do algebraic sum. When we have objects like this, we do algebraic sum. So we do the momentum of this one, mu, small m, multiplied by small u, okay, plus the momentum of this one, big M, multiplied by big U, okay. We can use this one to differentiate both. Or you can say M1 U1 plus M2 U2. Is that okay? You can use, or MA UA plus MB. You can use A and B for the object. It's up to whatever you want to use. So we can do that. But here I'm using small letter for this smaller object and big letter for this bigger object. Okay, object. So the total momentum before collision is to do the momentum of the small ball plus the momentum of the big ball. This one is not moving. The momentum will be zero. Why? Why is the momentum zero? Because it's in a fixed position. Only this one they show us that it's moving. they did show us any arrow to show that this one is moving, meaning this one is in a stationary position. So this is stationary position. The total momentum, the momentum of this object might just be zero. The momentum of this object might be zero. So the total momentum before collision will be depending on the momentum of this one that is moving. Okay, after collision, that's after impact. Then this one will be a positive u because it's still going to the direction with which this original one was going. So this one will be plus, but this one will be minus. So it will be m, small m times negative v because it's going in the opposite direction. Instead of this direction, it's now going this direction times minus v plus this one, the big M, multiplied by the V, big V. Okay? Because this one is going in the normal direction. This one does not have a negative. So this is the total momentum after collision. This is the total momentum after collision. For sticky object, we're going to have common velocity. If they stick together and they're moving together, they're going to have common velocity. So we just say M1 plus M2 multiplied by V, the common velocity, if they stick together. Okay, in that case, if they stick together, you have M1 or small m plus big M. Small m. Is it, like I said, depends what they are using. Here, we're using small m and big M. Small m plus big M multiplied by the V. If they stick together, they have a common velocity. This will be the total momentum after collision. But in this case, they don't stick together. This one is bouncing to the left, and this one continues to move to the right. This one is start to roll to the right. So this one become positive, this one will be negative. So this is the principle of conservation of momentum. We're going to look at example and see how they see the formula. The one with the small one has negative. Okay, so let's take a look at the tutorial for this one. Let's take a look at the tutorial for this second phase. Is that okay? Okay, let's quickly take a look at this tutorial. So let's have a look.
Here's a question for us to consider, and let's start by reading through the text in the question. The diagram shows a car approaching a solid wall at 15 meters per second. A crash test dummy of mass 77 kilograms is placed in the car to measure the potential effects of a car crash on the human body. Calculate the momentum of the dummy immediately before the crash. So let's have a look at the text and identify our command words. That's calculate, and we have to calculate the momentum, and importantly, the momentum of the dummy immediately before the crash. Now, just as a reminder of the theory, momentum is mass times velocity. We want the momentum of the dummy, and we've got the mass of the dummy over there. What's important to point out is that the dummy is inside the vehicle, so it will also have a speed or a velocity of 15 meters per second. Opening up our calculation window, just making our statement that momentum is mass times velocity. Just remember that momentum is represented in physics by lowercase p. Putting in our values, there's the mass of the dummy and the velocity of the dummy gives us 1155 kilogram meters per second. But remember now that momentum is a vector, so our complete answer is then 1155 kilograms meters per second to the right. So that's the same direction as the motion of the vehicle.
Okay, now quickly let's see the second. This is just for a question to calculate, that you can easily find questions like this. You can easily find questions like this in the exam, right? You can easily find questions like this in the exam. Now let's still take a look at the law of conservation of momentum that we've talked about. Okay, before that, let's do some work before we come back to the next tutorial. Is that okay? Let's do some basic work. Okay, so we've already explained this formula. We say here you go to the final momentum will be, because this is positive, you can write it first. It doesn't matter which one you write first. If you can write this first, and this one will become minus. So because they are going in opposite direction, so if I write mv, momentum of the big object, because it's going to the right, this negative will make this one to be negative. So I will have minus, this plus times minus is minus. I have minus mv. So this will be the total momentum after collision for these two objects. So it is the object that determines how the formula looks. Okay, you look at the object with the arrow showing the direction, you'll be able to tell the formula. Is that okay? Now let's move quickly. So this is what we have. Now let's move quickly. This is what we just did just now, and how it eventually becomes this. Now let's take a look at this question, worked example. So the diagram shows a car and a van just before and after the car collided with the van, which is initially at rest. This one, the diagram shows a car and a van just before and just after the car collided with the van, which is initially at rest. So the van was initially at rest, right? Now this this is the mass of the car and the speed of the car. This one, they didn't show you speed, means it's at rest actually. This one was initially at rest. So the momentum of this one will be 0, right? So we can use car and van. So here I'll be saying the momentum before collision, the momentum before collision, I will say m car. Okay, permit us to use that. M car, u car, the speed of the car. U car plus, why I say plus? Because it's going this way and this one is stationary. Plus m van, v van, u van. This is the total momentum before collision. And the total momentum after collision will only be determined by looking at what happened thereafter. This one keep going to the fourth, so it will be positive, and we don't know what this one. After collision, they did tell whether this one will move forward or backward. So, but we're going to derive that. Is that okay? We're going to derive that from the calculation. So this will be equal to the total momentum after collision. This is before. This one we've written is before collision. Before collision. Before, and this is after collision. After collision, the car was still going forward, right? After the collision, the car, because of this speed, was still going forward. Most likely this one is also going forward. Okay, so the car was still going forward, so we say m car, v car. Now we use v because after collision we use v, plus probably plus m van, v van. Okay, so this is the formula for this one. Now what we do first, we can calculate the total momentum before collision. Before collision, we have a mass of 990 kilogram. If the mass is not in kilogram, you have to convert to kilogram. 990 kilogram times the speed, which is 10, times 10. This one is stationary, plus, since this one is stationary, everything will be 0. Momentum will be 0. Right? The momentum will be 0. 4,200 times 0. Speed is 0, so therefore the momentum will be 0. 4,200 times 0 times 0, so the speed will be 0. The speed will be what? 0. So this one we get 9,900. If you multiply this, you get 9,900. 9,900 plus 0. Total will be 9,900. So the total momentum before collision, because the second vehicle is 0, the momentum from the the van is 0. So the total momentum before collision is 9,900 kilogram meter per second square. And sorry, kilogram meter per second, no square, okay? Kilogram meter per second. This is because it's speed, it's the unit of speed, meter per second. Kilogram meter per second. This is the total momentum before collision. This is going to be the total momentum before collision. Why? Because this one is 0. This one is 0. The momentum of this van, because the van was not moving, is 0. Okay? So let's see what they have. Yeah, that's what they have. So the momentum of the car before collision is going to sum up the total momentum before collision, because the momentum of the van is 0. The moment is supposed to be the momentum of the car plus the momentum of the van before collision. But since the van was not moving, once you're not moving, your momentum is 0. Once you are not moving, your momentum is what? 0. So the total momentum before collision is this, which we have calculated. Right? Now let's calculate the momentum after collision. Let's calculate the momentum. We go and look at the car. The momentum, we know the mass of this one, right? We know the mass of this and we know the mass of this one. We just put V in it. We are going to find the V. That's what they want us to calculate. Okay? So we calculate the mass, the momentum of this one after collision will be 990 times 2. 990 multiplied by 2, because the speed is 2 after collision. The speed is 2. So you say times 2. Times 2. We'll get 1,980, right? Is it 1,980? Yeah. We get 1,980 for this one. So plus this one, the mass is 4,200 times V. 4,200 times V. We don't know the because the question is going to ask us to calculate the speed of this one after collision. So we say times V. So 1,980 plus, we have 1,980 plus 4,200 V plus 4,200 V. This is the total momentum after collision. 4,200. This is the total momentum after collision. This is the total momentum after collision. 1,980 plus 4,200. Okay, so let's see. The first part, you get 1,980, which is this one of the car. Of the van is 4,200 V. So if you add them after collision, you get this, which is what we have calculated, what we have shown. Now to get the V, remember you want to get the speed of the total momentum before collision is equal to total momentum after collision. To get the V, the value of V, you must equate your calculation before collision and the calculation after collision. Right? We must equate the calculation before collision and the calculation after collision. So your momentum before collision, do you still remember? We had 9,900, right? The momentum before collision. We had 9,900. So we write it here. 9,900, which was our momentum, the total momentum before collision, because the van was 0, it didn't contribute, is equal to the momentum after collision. What's our momentum after collision? Our momentum after collision is 1,980 plus 4,200 V, because this is for the van. The mass of the van times the V. They just gave us the V. They didn't tell us the value. So you just say times V. Okay, this is the mass 990 times 2 for the car after collision. So you must bring both of them. So you say this is equals to 1,980 plus 4,200 plus 4,200 V plus 4,200 V. So we carry the 1,980 to this side. So subtract it from 9,900. 9,900 minus, you bring this one here, it's going to be minus. So if you bring it here, you subtract it. So I'm just going to do an arrow to show you that we're going to bring this one here and we're going to subtract it. So it becomes what? 7,920. So if I do that, on this side I have 7,920 on this side. How did we get that value? Because we move this one to this side, simple equation, remember, and we go to subtract it. When it comes here, we go to subtract. It's equal to 4,200. It's equal to 4,200 V. So we're going to divide both sides by 4,200. We're going to divide both sides by 4,200, so in order to get V. So to get V, I divide left and right by 4,200. So divide here by 4,200, you get V on the right, and divide the left by 4,200, we get the value. Okay, so here divide by 4,200. So this cancel this 4,200 cancel this 4,200. V will be equal to what? V equal to 7,920 divided by 4,200. We get 1.8, right? 1.88. So which is 1.9 V. So we get 1.9 meter per second. So the van will start to roll forward with a speed of 1.9 meter per second after collision. Because this is what they want you to calculate. The speed of the van after collision. The speed of this van after collision. So after collision, since this one is still going forward, definitely this one is going forward also. Because if this one is still going forward after he hit the van, it's still rolling forward, the van definitely is rolling forward. So they just want us to calculate the speed with which, that's why they put V here, the speed at which this van is moving forward. And that's what we have done using the law of conservation of momentum. Is that okay? So once you're able to do questions like this, you are damn good to go. You are damn good to go. Let's see if there's any other tutorial for this one. Once you're able to do any question with this similarity, you are damn good to. Let's take a look at one more question, and then we end the class. One more question, one more tutorial question, and then we end the class. Is that okay? Okay, so here is the question. Let's quickly see what we have. Okay.
Here's a rather wordy question for us to have a look at. So let's start by reading through it and making sense of what it is we're being asked to do. A toy train engine is rolling freely at a constant speed on a level piece of track. The train engine collides with a stationary truck and joins with it. Before the collision, the train engine is traveling at 0.30 meters per second and has a mass of 700 grams. If the stationary truck has a mass of 400 grams, calculate the speed of the joined engine and truck immediately after the collision. Okay, so first of all, let's identify our command word. So it's calculate. We're going to have to do a calculation of some kind, and we need to calculate the speed. We need to calculate the speed after this collision has taken place. Now, before we carry on and look at what else we've been given in the question, let's just talk about the strategy here. What have I got? I've got masses, I've got velocities, and I've got a collision. So where we have mass, velocities, and collision, we must be considering momentum. And we're going to be using momentum to help us solve this particular question. But before we start that, let's just have a look at some of the other important information in the question. So we've got that it's rolling freely, so that's the train engine is rolling freely. In other words, there's no motor or engine driving it along. It just has its own momentum. It's on a level piece of track, so once again, there's no other forces at play. The truck is stationary, so the truck is this little thing over here. That has no velocity before the collision. They're joined together. That's very, very important, and I'll elaborate on that a bit more once we get into the actual calculation. To make our life a little bit simpler, I've taken the information out of the question and actually put it on top of the diagram that we've been given. And you'll notice that I've converted the grams into kilograms. And that's a standard unit when we're working with momentum. So the engine has a mass of 0.7 kilograms and a speed of 0.3 meters per second, as was given in the question text. I've just put that arrow in to indicate that it's traveling in this direction. The truck itself has a mass of 0.4 kilograms, and we are told that it is stationary. So if it's stationary, it has no velocity. What I've done next is I've drawn a little sketch of what's happening after the collision has happened. Now, in an exam situation, I wouldn't recommend you go to the trouble of drawing a little sketch like this, but perhaps a little block diagram would suffice. But I think it's important in the context of this question for us to visualize what's happening before the collision, that's over there, and what's happening after the collision, and that's over there. So first of all, our two objects have joined together, and because they've joined together, I've added the masses together. There it is over there. The v is the unknown. That's the speed of these two things after the collision, and that's what we've been asked to work out. So I've got something happening before the collision, something happening after the collision, and that brings us to this idea of the principle of conservation of momentum. So here I've highlighted the theory, and we'll just read through it quickly, and I'll refer the theory back to the question. So in the absence of external forces, for example, friction, there we go, it's rolling freely, and there's no external force because the track is level, the total momentum of the system remains in place. That's a lovely sentence, but let's perhaps explain it a bit more, and it's explained very nicely over here. This means that in a collision, the sum of the moments before the collision will be the same as the sum of the moments after the collision. And we're going to use this principle of conservation of momentum to help us solve this problem. This is quite a detailed solution, so if you are not keeping up or you're not happy with what I've been saying, then just pause and rewind the video and go back again. It does all make sense in the end, so just stick with me. Here's my calculation window, and I'm going to start by working out the momentum of these two things, and this is referred to as a system. If you so these two things, the momentum of these two things before the collision, and here we go. So a little terminology: the mass of the engine and the initial velocity of the engine. So U represents initial velocity, and the mass of the truck and the initial velocity of the truck. That's the total momentum of the system before the collision. You can see that the truck has no momentum because it has no velocity. So the total momentum of this system is 0.21 kilogram meters per second. We're then going to apply the principle of conservation of momentum, and that states that whatever the momentum is here, it must be equal to the momentum over there. So here we go. I've taken the momentum, that's 0.21 kilogram meters per second, and that must be equal to the momentum of the engine and the momentum of the truck. Here I've changed to v, so it's final velocity representing the velocity after the collision. What's important to point out, and I did mention at the beginning of this question, is that the engine and the truck are actually joined together. So they have one velocity. They don't each have individual velocities. So I've simplified this expression here to say, well, it's just the mass of the two parts of the system, the engine and the truck, times their joint velocity, because at the end of the day, they're joined together. We can then simplify it even further. So the 1.1 kilograms, that's the joint mass of the two parts of the system times V. Some very simple mathematical manipulation will get you a velocity of 0.19 meters per second. And you can say, yeah, well, where is your direction? It's a velocity after all. The question only asked for the speed. Speed is a scalar quantity, so we only have to give the magnitude and not the direction.
Okay. If they even wanted the direction, if they wanted the direction, we would have, because they stick together, you already know the truck is going forward, right? So the direction will also be in the forward direction. If they wanted the direction, but they didn't want the direction because they are asking for the speed. They didn't ask you what is the velocity. They say what is the speed. So speed is a scalar quantity. Just calculate the value. It's good to go and put the unit 0.19 meter per second as it were. Is that okay? Okay. So you calculate the value and then you're good to go. So that's what we have for momentum for today. But we're going to part 2 of this. We're going to do impulse. Another class, okay? In another class, we're going to do the part 2, which is the impulse. Okay, so with this, we've come to the end of this class. Thank you for joining us. End it. Why is it not showing? Why do you remove this?
You didn't remove it. I escaped it for a second.
Fauzi, I don't know how to stop. You remove the stopping this thing. If you don't have it, why don't you don't